Today we're going to take a look at section 4.2, which is prime and composite numbers. So a reminder on both of those words, because I know you've seen them before, but a prime number is any positive integer with exactly two distinct positive divisors. Two divisors. So somebody give me an example of a prime number. 7. What are the factors of 7? 7 and 1. What else? 13. What are the factors of 13? 1 and 13. How about one more? 19. What are the factors of 19? 1 and 19. So the two distinct factors are always 1 and themselves. What's the smallest prime number? 2 is the correct answer. So let's address some of the things that you guys proposed as possibilities and say why they're not. We'll start with 0. 0 is actually divisible by everything. So that's no good. 1 is divisible by 1 and by itself. The problem with that is take a look back at the definition for prime. It does not have two factors that are distinct. It's only divisible by 1. So this one doesn't work either. Now, a very interesting note is that 2 is very different than the other numbers. How so? It's even, and it is the only even prime number. Any other prime number would actually be divisible by 2 as well, and so it would have more than 2 divisors. Okay? So if we have more than 2 distinct positive divisors, it's called composite. So we could go on for all day. Well, we could go on for all day with primes as well, but can you give me an example of a composite number? 12. It's divisible by 1 and 2 and 3 and 4 and 6 and 12, so that's lots more than 2 divisors. Another one. 6. So it's divisible by 1 and 2 and 3 and 6. That's 4 divisors. Let's give me one more. 8. Divisible by 1, 2, 4, and 8. What's the smallest composite number? It's 4. Good. 4 is divisible by 1, 2, and 4, so it would be composite as well. Good job. Factorization is any expression of a number in factored form. So for example, we would actually say that if we took 12 and we wrote it as 2 times 6, that's one factorization. If I wrote it as 4 times 3, that's another factorization, but these are both factorizations, because it says it's any expression in factored form. It doesn't have to say completely factored down in primes, okay? Just factored, broken down. And if it says prime factorization, then we actually need the factorization to only have prime numbers. So again, if I looked at 12 and I break it down, well, I could take, let me just take the 2 times 6 version of it, and then I would have 2 times 3. And when I do prime factorization, it is unique. You see, when I did factorization here, I had 2 possible answers. In fact, there were more than 2. But when I do prime factorization, it will have a unique structure. Now, we would not say, for instance, that if I did 2 times 3 times 2, that that's different, okay? So I don't mean the order has to be special, but the numbers themselves are unique. So what we're going to do next is we're going to do some different prime factorizations. I want to show you 2 different ways to do prime factorizations. One of them is maybe a little bit more prevalent, but it has some more potential for making errors. The other one has a little bit more structure, a little bit less free form, but you get a better structure in terms of getting accuracy in your answers. So they both have positives and negatives, all right? The first one is a factor tree. So I'll show it to you and then I'll ask you, I'm curious, which one of you, that was good English, right? Which ones of you have seen factor trees before? So a factor tree looks like this. We take our number that we are starting with and we break it down into any two numbers that when you multiply them together give you 23,660. And you usually look for something easy. For example, 10's a really nice number to divide this because it ends in 0. All right? So then I would have 2366 left. Neither of these numbers is prime, so I keep going. What will 10 divide into? 2 and 5, and 2 and 5 are both prime, right? So I'm done with the branches on that part of the tree. 2366. You may not look at that and just go, oh my goodness, I know what's next, but at the very least you know it's even, right? So we can divide it by 2. So let's start there. What would 2366 divided by 2 be? 1183 is correct. Now I know 1183 is not divisible by 2. So the next thing I would probably do at this point is try to figure out if 3 works. I know 5 doesn't work too, right? 5's not good. So does 3 work? No. I said 3 didn't work. I know 2 doesn't work. I know 5 doesn't work. 7 would be the next one. We don't have any rules for 7, but it works. What's the other factor when I divide by 7? 169. Do you recognize 169? Yeah, it's the square for 13, so it's 13 times 13. And at this point, I've broken everything down and they're all primes, correct? Here's the sort of potential problem for this. Even in the way I wrote it neat because that's kind of just my personality. Some of your structures probably don't look as neat and organized as mine. It's really easy at the end of these branches to lose one of those factors. So at the very least, I would encourage you that when you get to the ends of the branches, I've got the benefit of color on my screen, but you circle what you've got. Because what we're going to do next is we're going to write the factorization out. So do you remember when we did Venn diagrams and I said all the work looks like this, but then the answer is the shading? Well, we've done all the work now, and the answer is what I'm about to write out. It's taking these and combining them to say what you have left over, or left when you've done this. So I have 2 2's, so that's 2 squared, times, and we'll use dots for times just so we don't confuse it with our x's for variables. And then the 5 is next. We write them in ascending order, so 2 and then 5, and then 7 is the next one, times 7, times, and then I have 13, and it's 13 squared. How could I check to make sure that I have the right answer? Yeah, so I could take the answer and I could put this solution, my proposed solution, into my calculator, and I could ask my calculator to multiply this all out for me, right? And if it works out to being 23,660, then I got the right answer. Sound good? Okay, so I kind of feel like this, well, let me ask you first. Who's seen factor trees and used factor trees before? Okay, I think that's everybody. It's not always everybody in all my classes, but it's everybody or pretty close, okay? This has the drawback I already told you of losing an answer in the branches. It very much to me feels like when you're doing writing and you're brainstorming, it's, you know, the disorganized bubble diagram where you write everything out and then you try and figure out how things attach to each other, how they connect. So the next version I'm going to show you, which you may or may not have seen before, is more like the outline version. All right, it's the part of the essay when you're writing it that starts to look like it has more structure to it, and it feels a little bit more organized. So when I work with this one, this method, 23,660, what I'm going to do is I'm going to divide, but I'm only going to divide by primes. Okay, so over here in this method, I can divide by anything I want. I just only get to stop when I get primes. But in this method over here, this is a division ladder, is what I call it. So this division ladder, I only divide by primes. And I start with the smallest one possible. So I'm going to do my division. It's going to look like it's going upside down. 23,660 divides by the smallest number, what? You said it, Taryn. 2. Yeah, it's a 2. That's the smallest prime number. So what is 23,660 divided by 2? 11,830, right? Okay, good. Okay, well, will it divide by 2 again? So we do it again. Another 2. So what do I get if I divide this now by 2? 5,915. Will it divide by 2 again? No. Now, I want you to resist the urge to divide it by 5 because 5 is not the next prime number. That's the part where you're just like, but wait a minute, I saw the 5. Okay, it doesn't divide by 2. We all got that. Does it divide by 3? Yes, it does, actually. Didn't it? Did I not have a 3? I thought I had a 3 on the left. No, I don't. Okay, my bad. Okay, we would test it, though, to make sure that it didn't. That would be our next step. Then when it didn't, we would go on to our 5. So now I can divide by 5. What do I get? 1183. Okay, will that divide by 5? No. Now notice I didn't ask you if it would divide by 2s or 3s. I know it won't because I already have gotten to the point where I know there are no more 2s because I did them and I ran out of that possibility. So I don't have to keep asking myself every time, how about this piece? Will it divide by 2 now or will it divide by 3 now? It won't. I already tried those numbers and they stopped working. And now I've tried 7s or 5s and they've stopped working. So 7 would be my next one. We know it works because we did it just a minute ago and we got 169. If you hadn't done it, you would have done it now. And then at the point when you got to 169, you probably recognize 13 and 13. Those are the primes. If you didn't and you tried to do 11, you would find it didn't work because that's the one that's in between there. The cool thing and the thing that is probably my favorite about this, why maybe I like this so much, is because all the answers are right here in order. That was supposed to be a highlighter. Let's try that again. They're all here in order. 2s are grouped together. The 5s are grouped together. I can't lose an answer along the way, you know, because it was the end of a branch and I forgot to circle it. So that's actually the reason that I prefer this method, is because the answer itself is easier to see when I'm done. So I've got 2 squared times 5 times 7 times 13 squared. Now, as you're working, your book is not going to tell you how to do these. At least I don't think it does, or if it does, it doesn't do it most of the time. So you can pick which way you do it. So if you absolutely love factor trees, you're not hurting my feelings at all. Use your factor trees, just be careful, okay? If you want to give this a try and do that instead. But please understand that if you have children and you're trying to teach, not children, students. If you have students and you're trying to teach them this, you know, and they keep losing factors at the end of their factor trees, it might be time to try something different, all right? Or if they just can't handle the free-form thinking of a factor tree, it might be time to try something different. Or if you decide that you're in love with this new one that I just showed you, and your kid is like, but I really wanted to divide by 3, and you're like, no, you have to divide by 2, or whatever. It doesn't matter that much. It's not worth the argument of the structure part of it, okay? So just know that you have some options here. All right, I'm going to show you a couple others. The next 2 that we're going to look at look different when they start. So how is this one different than part A? What do you notice immediately? Exponents. I would encourage you not to multiply this out. That is counterproductive. This is already partially factored. Do you guys see that? I mean, I've already got some exponents in it, just like I had exponents over here when I ended, right? So don't go backwards in the process by trying to multiply it out. Instead, what I'd like for us to do is to look at the numbers that do have the exponents and factor them. Okay, we can still use factor trees, we can still use division ladders, whatever you want to use, but we're going to factor them. So I'll use factor trees for the first one, and then we'll use a division one for the second one. If I do 16, you probably are going to say, oh, that's 4 times 4, and then your 4s are 2 times 2 and 2 times 2, right? I'm going to move on to my 81. This is one of those places where your division algorithm or your division ladder might feel awkward. You might look at this and go, but I really want to divide by 9. I mean, it divides by 9, right? Like, obviously, we all know that. But if you're using the division algorithm, it doesn't divide by 2, but it does divide by 3. Do you know what 81 divided by 3 is? It is 27. And then 27 divided by 3 is 9. 9 divided by 3 is 3. And then I get one more 3. And then, of course, 6 is just 2 times 3. So no matter how you write that down, it's not a very long process. Okay, so what does that mean? Well, it means that I'm going to take what I have here and I'm going to rewrite them. And when I rewrite them, the 4 the 4 and the 6 will be present after each of the factors. So for instance, number 16, 16 is 2 to the 4th. But that 16 had another power of 4. So this is 2 to the 4th to the 4th. The 81 is also 3 to the 4th. But the 81 had a power of 4 on it as well. The 6 is 2 times 3, and it has a power of 6. Okay. What we're going to do next is we're going to use the properties of exponents that we talked about back in Chapter 3 to simplify and combine like pieces. So, 2 to the 4th to the 4th, starting at the beginning. What is that? What happens when you have a 4 to the 4 like that? It is 2 to the 16. When you have a power raised to a power, you multiply exponents. So this is 2 to the 16th. And that means obviously then I have 3 to the 16th as well, right? Yeah. What about when I have 2 times 3 to the 6th? What power rule does that employ? Like a distributive one, right? So I would have 2 to the 6th and I would have 3 to the 6th. Now, you'll notice that I'm being a little bit sloppy. There's no dots between things. Because of the way that they're exponential here, it's understood to be there. If you're concerned or uncomfortable with it, I'll put them back in, which is fine with me too. I need them in primes, okay? So do you see any that match? Yeah, this 2 to the 16th and this 2 to the 6th. So they're 2 to the what power? 22. How did you get 22? You added the exponents, exactly. How about the 3 to the 16th and the 3 to the 6th? You'd have a 3 to the 22. Very nicely done. And that would be your factored form, prime factorization anyway. Okay, so we're going to change it a little bit more. I still see exponents like I did in the last problem, but what do I see now that I didn't have before? Addition. Okay? So again, it is not in your best interest. In fact, if you do this by this method, I will just not give you points on a test for it, to multiply this out and then to refactor. That is very counterproductive. Okay? So what should you do? Well, you should look at them and you should see what they have in common, kind of like we did in the previous problem. These all happen to have prime bases. Did you see that? 2, 3, 5, 7. They're all, I mean, all the bases are 2, 3, and 7 are all primes, right? So I don't actually have to factor anything like I did over here with the 16, the 81, and the 6. But I do want to notice what they have in common. So they both have a 2 to some power, agreed? So I'm going to write that down, just the 2 part down for the moment, and put a dot. They also have a 3. Right? So I'm going to write the 3 down and put a dot. And then they also have a 7. So I'm going to write the 7 down with a dot. What I want to go back and do now is I want to go back and put the highest exponent is that they have in common. So for instance, on the 2's, this one is 2 squared and this one is 2 to the 4th. What's the biggest number of 2's that they both have? 2. The first one is 2 squared, so it has 2 2's. The second one is 2 to the 4th, so it has 4 2's. So I've got 2 squared. The next piece, 3 to the 5th and 3 to the 4th. What's the most number of 3's they have in common? 4 of them, so I'm going to put 3 to the 4th. And then the last piece is 7 to the 55. On both of them are the same, right? So I'm going to put 7 to 55. Ariel? Yes. Because this one doesn't have 3 2's. It only has 2 2's. Yeah. Okay. Now, I'm going to go back up here because I've got too much going on. And let's take a look at what happened. We'll do it with the 2's first. If I take a 2 squared and I take out, factor, divide out a 2 squared, what do I have left? What What do I have left, Cassidy? I have a 1, right? What is 2 squared divided by 2 squared? It's 1. It's not 0, right? It's 1. It says division. I'm going to leave that 1 there and put a plus sign because the plus sign is still carrying on, okay? Now, look at the second piece, 2 to the 4th here, like the second one with a 2. When I take 2 to the 4th and I divide by 2 squared, how many 2's do I have left? 2. I have a 2 squared left here. So I'm just writing in the leftover pieces. This is the leftover pieces of the 2's. A 1 and a 2 squared. How about for my 3's? This one is 3 to the 5th, and I took out 3 to the 4th. How many 3's do I have left? 1 3. That's 3, like this, right? So there's a times the 3. Over here, I had a 3 to the 4th, and I took out a 3 to the 4th. What do I have left? I have just the number 1, kind of like I did on the 2's in the first piece. And now just for the sake of showing it, so that when you look back at this later you know we did it, we do the same thing, or could do the same thing with a 7 to the 55. 7 to the 55th divided by 7 to the 55th is 1. And it happens on both of these pieces. So the first part of this is done. I don't have to do anything more with it at the moment. It's all in beautifully factored form. But this second piece, I need to clean it up. 1 times 3 times 1 is 3. 2 squared is 4 times 1 times 1, so that's 4. But then I have 3 times 4. I'm sorry, 3 plus 4, which is what? It's actually 7. So at the end here, I have times another 7. Can I consolidate that? I can. So this is 2 squared times 3 to the 4th times 7 to the 56th when I'm done. It's so important that you remember that when you divide, you get 1. And even as I'm saying it right now, you're all like, well, yes, I know. When I divide 7 by 7, I get 1. I know that. I know, and I know you know that. But half of you are going to do it wrong when I get to the test and ask you a similar question. You're just going to forget. So please write yourself a note, star it, bold it, something that this is important. It's a very commonly missed problem. Kayla.
Okay, so whenever you got, okay, so I know you got 1 and then times the 3. Said 3 because you only have 1 3 left, so you didn't put it when you put the actual number 3.
Right.
Okay.
So it's like 3 to the power 1,
Okay.
if it helps you to think of it that way.
Okay. And
Yes.
then for the 2 squared, you did that for the same reason?
Yes, because there were 4 2's, so I have 2 of them left. So I have
Okay.
2 squared left. Yes. Okay, any other questions on this one? Okay. Let's see. We'll go just a little bit further. We've got just a few more minutes left. Here's the thing. Anytime somebody puts the phrase fundamental theorem on it, it means it's really important. So this is a fundamental theorem of arithmetic, and it says, each composite number can be written as a product of primes in one and only one way, except for the order of the primes. I actually already told you that earlier. Our very first slide for our day, I said it in different words. I talked about the number 12 can be factored in more than one way, but it only has one way that it can be factored into primes. And that's what this fundamental theorem says. There's only one way to break it down, and one unique description of primes. Okay, let's take a look at a few theorems and how they apply and how they're used. Theorem 414 says, if D is a divisor of n, then n divided by D is a divisor of n. Another way of saying this is that factors occur in pairs. and I'll give you an example. 3 divides 24, right? Yeah, it does. 3 divides 24. What is 24 divided by 3? 8. Well, that means that 8 also then divides 24. That's what this theorem literally says. That whatever you get when you do the division is also a divisor. Now, my sort of rewritten summary here about it occurring pairs says that if you took 24 and you started listing what it divides by, you could always list them in pairs. So for example, you could do 1 times 24. You could do 2 times 12. We already said 3 times 8. What else is there? 4 times 6. They always occur in pairs. So if one of the numbers divides the factor 24, or whatever you have, the other one will as well. These occur in pairs. Sometimes we want to know if a factor or if a number is composite or if it's prime. And we can sometimes see pretty quickly, oh, it's even, I know it divides by 2. Oh, it ends in a 5, I know it divides by 5. But like when we got to 1183, I don't think any of us looked at it and goes, it divides by 7. I know it. I know I didn't, and I've got notes, and I wasn't looking at them, but I still didn't know it, right? I mean, that's not one that I can look at and say for sure. And if it didn't divide by 7, and I then tried 11, and it didn't divide by 11, and then I tried 13, and it didn't divide by 13, there comes a point when I have to decide, how far do I have to go before I can stop trying numbers? Make sense? That's what our next theorem actually talks about. These two theorems actually are very related. So the first one says, if n is a composite number, if it is composite, then it will have a prime factor such that the prime factor squared is less than or equal to n. And then theorem 416 says, if n is a whole number greater than 1, and it doesn't have a number that will do this, then it's called prime. And the actual logistics of what does this mean for me is that if I have a funny number, we'll do the next example just because that's what it is anyway. Have a funny number, 967. Do you know right now if 967 is prime? And if I don't look at my paper, I haven't yet, I'm not sure either. But this tells me how far I have to go to look. And here's what it says. It says that if it does have a prime number as a factor, then that prime number, so let's say it's, let me just say for a moment here, 5 squared. If it were divisible by 5, then 5 squared would be less than, what is it, 967. Okay? So I'm looking for some number that when I square it, it's less than 967. So what do I do to do that? Well, I can take 967 and I can take its square root. So we need an approximation for it actually. 1 decimal is sufficient. What is a square root approximately of 967? 31.1. What that means is that I don't have to test anything bigger than 31. I mean, that's a pretty good cap for a number that's 900 something, isn't it? There's not that many prime numbers less than 31 to check. So we would check them, right? And so the question here just simply says, what is the greatest prime number that you must check? So what is the biggest prime number smaller than 31.1? What is it? It's 31. It's 31. Even if I'd taken my square root and I had gotten 32.67, that's my square root value, it would still be 31 because 32 is not prime. It's smaller than it, but it's not prime. You still have to go with the prime number that's smaller than it. All right, we will pick up with example 3 next time.